Welcome to a quick overview of our unit on fluids. One of the first things that we covered in this unit on fluids was the particle theory, and so we should be familiar with how the particles are arranged in various states of matter: solid, liquid, and gas. We should know how quickly the particles move in the three states of matter: solid, liquid, and gas. And thirdly, we should know how strongly attracted the particles are in the three states of matter. Next, here's a brief overview of the particle theory as you remember it hopefully in grade 7. All matter is made up of these tiny particles that we can't see. The particles are always moving. We call that their kinetic energy. They're moving fastest in gases, they're moving a little more slowly in liquids, and they're barely vibrating in solids. We should know that when we add heat to matter, the particles move around faster, we weaken their attractive forces, and they become a little bit more fluid. And we should know about the different spaces between the particles. Next, we talked about viscosity and how some substances flow. Solids do not flow and are basically considered zero viscosity. However, liquids and gases do have a viscosity, and it partly has to do with how closely packed the particles are. But it's not just that, because this is density, and there's more to viscosity than just the density of the fluid. The reason for that is if we look at the viscosity of oil versus water, water has a higher density than oil, but it has a lower viscosity. Also, liquids, when we heat them, their particles move farther apart and they become less dense. Whereas in gases, it gets a little more complicated. The viscosity of a gas actually increases, which means they flow slower when we heat them up. And it has to do with what we call a sticking phenomenon. So when oxygen or nitrogen particles speed up, they move around faster, they collide more, and on their collisions, there's a bit of a stick that goes on, which means when they move faster, they stick a little more, and their viscosity, believe it or not, gets higher. Next, we should know the difference between mass and weight and the relationship between mass and weight on Earth. 1 kilogram of mass is equal to approximately 10 newtons of weight. We should know how we measure weight with a spring scale and how we measure mass with what's called a balance scale. We should know that weight is the force of gravity and it'll change, whereas mass doesn't change, it's the amount of matter. We should know how to measure volume depending on what we have. Volume of a liquid, we use a graduated cylinder. Volume of regular shaped solids, we would use length times width times height. Volume of strange or irregular shaped solids, we would use the method of displacement. So in this case, if we have 7 mils before we add the object, and then we add the object and it goes up by 2 mils, that means the volume of this object is 2 mils. And if we have great big, huge things that don't fit into graduated cylinders, then we would use, of course, an overflow can and then a graduated cylinder. We should know how to calculate density. It's the mass of the object divided by the volume. Here's an example of how we might find the density of a rock or something like that. So we need its volume, so we use displacement. We could use cotton to dip it in here, so 75 before, we dunk it in and it goes up to 90. What's the difference between 90 and 75? 15 mils. So we put the object on a balance scale and we now have its mass. So we take its mass and we divide it by the volume to get the density. We should know what a hydrometer is. It's a device that floats and has calibration markings to tell what the density is of a liquid. And as you notice, the higher up it floats, so right now it's at 0.10. If it floats higher, that means that this liquid has a higher density. The lower down the hydrometer sits in the fluid, the lower the density. So if it sat right there, we'd know it was pure water because pure water has a density of 1.0. So once again, the height that the hydrometer floats determines the density of the liquid. The lower down, the less dense, the higher up the hydrometer sits, the more dense the fluid. So here's an example. This is a hydrometer sitting in salt water. So this is salt water. And notice how high up the hydrometer is sitting. And this is a hydrometer in, I think it's pure water, and it's lower down. So there's pure water. Let's talk about buoyancy. Every fluid, so that's not a solid, has what's called an upward push or a buoyant force. And the greater the density of the fluid, the greater its upward push or buoyant force. And so things that float in liquids or gases, we need to consider two forces. The yellow arrow is showing you the buoyant force. So the buoyant force. And the red arrow is showing you the force of gravity. There are three possible situations that can occur when we have a fluid and something floating. One, it could rise up, which means the buoyant force is stronger than the force of gravity. We call this positive buoyancy. The next would be the force of the fluid, the buoyant force, the yellow arrow, and the red arrow are the same. We would call that neutral buoyancy, and it would hover. And if the object sinks, that means the upward push of the fluid, which is the buoyant force, is smaller than the force of gravity, and so it would sink, or we call that negative buoyancy. Archimedes figured this out too. And so Archimedes' principle states that the buoyant force of a submerged object is equal to the weight of the fluid that is displaced. So let's look at the picture here. Here's a rock, and in air the rock is 0.67 newtons. In the liquid, we dunk it in, it displaces some water here, and now look, it's 0.4. The difference between these two on the force meter tells us how much the liquid is helping hold up the rock. Remember, there's two forces. One is the buoyant force, and the other is the force of gravity. In the case of a rock, we know it sinks. And so the force of gravity is going to be stronger than the upward push. How much is this? 0.67 minus 0.4. So that's 0.27 newtons. That's how much the liquid's helping. Well, what do you notice? If we take the water that the rock spilled out or displaced and we weigh it, look at 0.37 before, 0.1 after. What's the difference here? The same, 0.27 newtons. Now this object sinks. However, what if the rock had a smaller weight, like what if it had 0.1? Now it would be positively buoyant because the liquid's pushing with 0.27. Objects' buoyant force and their density are totally related. So if you look at this, corn syrup has a density of 0.2128 and so on. We could tell if we mixed all these liquids together where they would be in a column. The heaviest liquid would be at the bottom, so this corn syrup would be there. Then glycerol would be here. Then water would be here with red food coloring. Then vegetable oil, and then the motor oil would sit on the top because it's the least dense. This guy's just showing you how to calculate buoyant force. Let's talk about pressure. Pressure is equal to force in newtons divided by the area, which should be in meters squared if we want it to be equal to what we call a Pascal, a PA. So if you have it in centimeters squared, you'd want to convert it to make sure that it was in PA. This is a barometer. It measures air pressure. As air pressure goes down, usually this is associated with poor weather. So poor weather, a storm. As air pressure goes up, so you get high air pressure, that's usually associated with warmer, nice weather. What's the pressure in this chamber? Well, 5 newtons divided by 2.5. The pressure in here would be 2. Not 2 pascals though, because remember this is centimeters squared. We need to know the difference between these two fluids. Liquids are virtually incompressible, and so they make good liquids for hydraulic presses. Gases we can compress or squish down. In this picture you can see that. And so we usually use it for pneumatic devices, which we'll talk about in a minute. Pneumatics. Let's keep talking about pressure, atmospheric pressure. So it's based on the column of air. And so when you're at sea level, atmospheric pressure is pretty high. Something around 105 kilopascals is pretty close to normal 105 kPa. But as you climb up a mountain, the column of air gets smaller and smaller, and so does air pressure. So it might be, depending on the height of the mountain, it could be as low as 60 kPa due to the smaller column of air. Water works different. So here's the ocean. As we go deeper into the ocean, the column of water gets bigger, and that pushes down, and therefore higher water pressure as you go deeper in the ocean. Let's talk about how we calculate the pressure at the bottom of a tank. And so here's our tank. We have to step 1, we find the volume, length times width times height, so 50 times 10 times 20, and that's 10,000 centimeters cubed. Next, we find the mass of the water. Remember, on Earth, water has 1 gram per centimeter, so that's simply 10,000 grams. Then we convert it to weight. 100 grams is 1 newton, and so that's 10,000 grams is equal to 100 newtons. Now we find the surface area. We have to convert, so it's in meters squared, so we can convert to PA. So we got to convert these to 0.5 and 0.1. So 0.5 times 0.1 is 0.05. Now we go to pressure, and pressure is the force, which is this, 100 newtons, divided by the surface area, which is this. And so there's our pressure, 2,000 PA, or 2 kPa. Hydraulics. This over this is equal to this over this in a hydraulic press because of what something's called Pascal's law. Pascal said that the pressure inside here, 0.3, will always stay the same. So this on this side has to equal 0.3 and this on this side. And so if we know that, as long as the pressure or the force over the area here is equal to 0.3 and the force over the area here, then we're okay. And pneumatics, this has to do with gases under pressure. And so our lungs are pneumatics, a hydraulic or a jackhammer, etc. We should know Wim is